All right, so our next unit here is about what's called simple harmonic motion. And our first thing that we're going to talk about in simple harmonic motion is what's called Hooke's law. Our target here that we want to be able to do by the end of this lesson is to be able to explain how force, velocity, and acceleration change as an object vibrates with simple harmonic motion. So let's go ahead and let's talk about what is simple harmonic motion and what is Hooke's law. Well, the first thing, the kinds of motion that we're going to talk about in this unit and coming up is what's called periodic motion. It's called periodic. The word periodic you might recognize from chemistry. It was in the periodic table, right? If you remember, we call it the periodic table because the properties of those elements repeat in a regular pattern. And that's what the word periodic means. It means something that repeats in a regular pattern. Periodic motion is the motion of a thing that repeats in a predictable way, right? Periodically. One of the simplest kinds of periodic motion that we're going to talk about in this unit is a mass on a spring. And you can see a little diagram, mass on a spring kind of vibrating back and forth, right? When the spring is stretched or compressed, the mass will kind of vibrate back and forth around what's called the equilibrium position. That equilibrium position is where that mass would be if it wasn't moving. If this whole thing just came to a stop, where would that mass end up being? It's called the equilibrium position. Okay, at the equilibrium position, the mass's velocity will be the greatest as you see it moving back and forth. Let's look at this other diagram here, right? You can see on this diagram the equilibrium position is marked by that line there, and you can see the mass vibrating back and forth to either side of that line. There's also an arrow there, a red arrow, that's showing you how much force and which direction the spring puts a force on the mass, and then a blue arrow there telling you how far the object is from its equilibrium position. So as the object crosses that equilibrium position, its velocity is the highest it's going to be, and then when it gets past that equilibrium position, the spring will slow it down until it gets to the furthest from the equilibrium position. At that point where it's furthest from the equilibrium position, it will stop and then start moving in the other direction, right? And this kind of motion is what we call simple harmonic motion. One thing about this mass on a spring example is it's really not that difficult to calculate how much force the spring is applying to the mass at any particular point in time. We have a law named Hooke's law, named after a scientist by the name of Robert Hooke. You can see Hooke's law here. Hooke's law says that the force acting on the mass is equal to minus kx. Now the force there is a force that's measured in newtons, of course. The x there is the mass's distance from the equilibrium position, and then that k is the spring constant. Now we've seen spring constant before. If you think back to when we talked about potential energy, we learned about elastic potential energy, and the spring constant was a part of that. And here it is again with something having to do with springs, right? So the spring constant, kind of a measure of how springy or stretchy that spring is. It doesn't have to be a spring, it could be a rubber band or a bungee cord or something along those lines. The spring constant is measured in newtons per meter. So F, the force, is equal to minus K, the spring constant, times X, the distance from the equilibrium position. So it's a fairly simple law. That negative sign in there tells us that the force and the displacement are going to be in opposite directions. So if the mass is to the right of the equilibrium position, then the spring will be pulling it back towards the left. So the force and the displacement are in opposite directions. Just kind of a side note here about Robert Hooke, kind of an interesting story. Robert Hooke was a rival of Isaac Newton, right? They didn't get along. I don't think either one of them actually got along with anybody, but they didn't get along with each other. They both accused each other of stealing each other's discoveries, and it's kind of interesting. People from the time, you can especially important people who have scientific laws named after them, usually you can find a picture of them. Somebody painted them at some point. And people may have painted Robert Hooke, but there are no surviving pictures of him. And the people who knew him and wrote about him at the time described him as particularly ugly. So, yeah, Robert Hooke, there you go. Maybe that's why those paintings didn't survive to the modern day. Who knows? Or maybe they were just like being mean and being bullies because people didn't, they didn't get along with them. Who knows? Let's have a look at a problem, a kind of example of the kind of thing we might see in our problems here. So this one, it says, we've got a picture there, and it says if a mass of 0.55 kilograms attached to a vertical spring stretches the spring 2.0 centimeters from its original equilibrium position, what is the spring constant? So we are going to use our Hooke's law to find the spring constant. Okay, this one's got a little bit of trickiness in this. Okay, it's got a little bit of trickiness because it doesn't tell you the force. Okay, but we can look at the picture and we can understand what's going on, and we can see that the force that's pulling this mass down is the force of gravity, and we know how to calculate the force of gravity. So the force here is going to be the mass times g, the force of gravity, right? Okay, it tells us the mass. It told us it was 0.55 kilograms, and then we know g, 9.81 meters per second squared. So if we go ahead and we can calculate the force, grab my calculator out of here. And I get, what do we want? Two significant figures. I get 5.4 newtons. Okay. And then let's see. The problem tells us that the displacement, how far it's stretched, tells us this is 2 centimeters, 2.0 centimeters. And of course, we don't want to do our math in centimeters. We want it to be in meters. So let's go ahead and change that into meters. And centi means 10 to the minus 2. So I'm just going to write 2.0 times 10 to the minus 2. All right. Then we can go ahead and put our numbers into the equation and solve for k. So the force was 5.4. With the negative sign, k is our spring constant that we're looking for, and x is 2.0 times 10 to the minus 2. Okay. Now let's see. All we really have to do is divide by that distance there. So let's take 5.4 divided by 2.0 times 10 to the minus 2. And there I get, let's see, we want two significant figures. So I get 270. Okay. Now let's talk about the negatives for a second here. We learned at some point that g was negative. I mean, up here we could have put negative, and then our, let's see, our force would have been a negative, and then here we would get a positive answer, right? I didn't do that. That's okay. Here I actually got negative 270. Really, all that sign is, we have to understand that the force and the displacement are going to be in opposite directions, right? So here, perhaps I should have put them on there. But if I didn't, that's okay. I understand that the spring constant should come out to be a positive number. Okay. So now the units for spring constant are newtons per meter. So I'm going to put newtons per meter. So there we go. There's a little bit about Hooke's law, much simpler than some of the stuff that we were doing, especially towards the end of the last unit. From here, we're after talking about Hooke's law, next time we'll talk about pendulums. Beyond that, we'll talk about waves, and then sound, and then light, and lots of periodic kind of things. So hopefully this helps us be able to explain how force, velocity, and acceleration change as an object vibrates with simple harmonic motion. So until next time, take it easy.